Yeah, students, today we are going to start with the new chapter, chapter number 6. It's called Newton's Laws of Motion. In other words, it's written here 3 laws of motion. So, units and dimensions is the first chapter. Next one is we have motion in 1 and 2 dimension. It is called motion in straight line, and a plane is called second chapter. This is the third chapter is given here. In the actual lineup of 10 chapters, but it has been subdivided into many chapters, so it is called 6th chapter. We always call it as laws of motion only. We don't really use Newton's the word of Newton every time. So if you look at the syllabus is given here. Please take a look on it, and we will be going ahead of the basic concepts of many things. For this particular chapter, please write in the notebook Newton's laws of motion, and you will not write anything in your notebook. You're going to learn from the book. So I'm going to underline many things, or I'm going to shave. These are the things that you need to keep it in mind. Please go through the book, take a book with you, and start reading along with the video. And that's it. If you can just bracket everything and learn everything, whatever you are listening today, so that it will be easy for you to understand this topic. So this whole chapter will finally concentrate on one very important word called force. Force is the main aspect that we'll be seeing in the whole of this one. So general concept of force is given here. So this definition you have been learning from grade 3 of grade 4. So what is force? Force is an external effort in the form of push or pull, which either changes or tends to change the state of rest or uniform motion of a body along a straight line. You know this definition. It is basically a push or pull. It is an effort. It is an external effort done to a body. So whenever you are giving an external effort, there could be two possibilities. One is the force which is given because a body is getting connected with something else. For example, there is a block. You wanted to move this block, so you are there to push this one physically. So you push this one physically, so this body goes. So that means there's a contact which has been there. You give a force with a point of contact. So that's a way in which the force can be given also. There is also another way, without contact also the force can be applied. I think you can quickly think about so many other examples. Suppose there is a magnet here. It is called North and South Pole, and you have another block that is a metal body. You wanted to move this one closer to this one. What to do? Keep the magnet close by. Automatically the force is applied if this body moves towards this one. Without point of contact also a force can be applied. So there are two varieties are there. If you look at this one, contact forces, non-contact forces. You can read this one. Force comes into play on an actual contact between two bodies under consideration are called contact forces. The next one is the forces which come into play without any physical contact between bodies under consideration is called non-contact forces. You can just go through several things: frictional force, tensile force. These all things are contact forces. Electrical and magnetic and gravitation, these are all non-contact forces. The next one is the most important concept, which will be called as inertia. So what is inertia? You already learned this one in 9th standard quite thoroughly, but it is worth repeating this one here. The inherent means the property by virtue. What does property by virtue means? Naturally. The inherent property, it is naturally, that's the way God has created. The inherent property of all the objects that they do not change the state of rest or of uniform motion along a straight line path unless acted upon an external force is called inertia. So you can read this one. So what are the various questions are given? You can just answer those going. The natural phenomenon which God has put in every body is you need an external agency to change the state of rest. If it is always at rest, it will be at rest. So objects, they do not change themselves. It needs something else externally, it needs something else to change the state of rest. So what is that before itself? Before giving some external agency is coming, what is happening is there's a basic property of inertia which is there, that it will be rest means it will be constantly at rest. So uniform motion means it will be constantly going in a uniform motion unless and until acted upon an external force. So force is given here, inertia is given here. Some basic way of defining your in this age, you all have less inertia, you have less inertia or more inertia. What do you have? Let me give you some example. I think you all have more inertia. What is more inertia? The property of unable to change state of rest. What is unable to change the property of rest? If you consider a 11th standard child, the property of state of rest is so much common. A body continues to be in a state of rest always. Suppose you are in sleeping mode, you sleep off morning 6 o'clock, 7 o'clock, 8 o'clock. You want to sleep, you want to continue to sleep at all, continuously. You don't have to get up. Suppose if nobody wakes you up, you have so much of inertia, more amount of inertia, your body continues to be at the state of same rest. Constantly, unless and until somebody constantly comes and wakes you up. Am I right? Are you able to little more understand the word inertia? Inertia means you are unable to really get up. Am I right? So that's what it is. So inertia means you have so much of inertia. What's the inertia is? I will constantly keep on sleeping if I am sleeping. Now, so for example, motion. Motion means, suppose you are playing a game, playing a football game or playing a mobile game, and you are on the state of motion. You are constantly playing, and you don't want to stop. Constantly you keep on going on. Inertia is very high. When you start the motion, it doesn't stop. Maybe TV viewing. Oh, this much only. I keep on watching. One more, another 10 minutes. You keep on watching. Another 10 minutes. You keep on watching. It goes on and on. If it is motion, it goes on and on. So that is more inertia. Now, let us consider, do we have less inertia or more inertia? If you are unable to change anything which you are doing, that means you have more inertia. Let us consider what is less inertia means. Maybe studying means less inertia. You study and then immediately you want to get distracted and go to the next one. So something else is pulling you. So it's just kind of an example to make you to understand inertia. So anything that is you are doing and you continue to keep on doing, that becomes more and more inertia to me, something like that. But in actual sense here, it is just something off the topic I'm just giving. But actual sense here is a body will be at rest. It will continue to be at rest. The body is moving. It will continue to keep on moving. External forces needed to change it. So there are three types: inertia of rest, inertia of motion, and inertia of direction. So there are three things. Suppose if it is at rest, it will continue to be at rest. So the first topic is inertia of rest. It is inability of a body not to change by itself its position of rest. So suppose you keep a notebook on a table. A book is there, physics book is there, lying on the table. So it will lie on the table continuously. It will not change at all unless and until there is a test is there and you need to take it and start learning it. So that is inertia of rest. So some of the examples are given here. Please read this example. You can make yourself a little more aware of this one. Suppose a bus is there and all the passengers sitting here. So and all of a sudden the driver accelerates the bus. as soon as he accelerates so quickly, then what happens to every passenger who is sitting here? The passenger will fall back. He will just lean backwards. Have you seen that one? Why do we lean backwards? The bus is moving. All of a sudden it's moving, but you are at rest. You wanted to continue to be at rest. So you lean backwards. So that's the example it's given here. When a bus or a train starts suddenly, a passenger standing inside leans backwards. Especially people are sitting or standing, all of them lean backwards when the bus is moving, because you are at rest. You wanted to continue to be at rest. There are a few other examples in this one. Hanging carpet is beaten with a stick so that dust particles can come. It is cleared. Suppose you have a carpet. So what happens on this one? You just put a carpet here and you beat it nicely with a stick. What happens when you beat it? The carpet goes this side, and again when you beat nicely again and again, the carpet goes this direction, and the dust particles which is there, it continues to remain at rest, so it just falls down. But the carpet has moved here. The carpet has moved here, but the dust particles continue to remain, and it just falls on the ground. That's the way it becomes. When a card is carrying a coin is placed on the bottle, it is flipped away quickly with a finger. The coin falls into the bottle. So this one example you would have already heard. When there is a card is kept here, and then there is a coin which is kept here, just push this one quite quickly, immediately this coin will fall down. So because it is at rest, it will continue to be at rest. You need to do it very, very quickly. You just pull it so fast, it will just drop it inside. So that's what it is. And then these are the mango season, you wanted to take some mangoes from the tree. What do? You are unable to climb up, so you start shaking the branches. So that's what you do. And when you shake the branches of the mango tree, the mango falls down because it gets disconnected. It wanted to be at the state of rest, so it just disconnected and it falls down. A bullet fired against the window glass makes a clear hole in the glass without cracking it. Sometimes it just passes inside because it is the state of rest it wanted to maintain, so it just goes inside without cracking everything. The next one is the inertia of motion. Inertia of motion we are going to see. The inability of a body not to change by itself its state of uniform motion along a straight line. Now look at this one. Underlining word is uniform motion. It is not written just motion. What is uniform motion? That means acceleration is zero. You are not changing the acceleration. You are not changing the velocity. Velocity is always same. That means acceleration is zero means velocity is same. So a body is moving means it continuously moves. Now you can say, sir, I take anything, a ball is there, and I roll it on the floor, and the ball is going to finally eventually stop. How can you say the ball will keep on going? It should keep on going. No, but it doesn't go, because that you already know there is a frictional force which is there applied between the ball and the floor, so the ball stops. So anyhow, there is a frictional force is applied here. That's the reason it stops. Had it been there is no friction at all, the body will continuously keep on moving. That is the inertia of motion. Examples: when a bus is constantly on the motion and immediately you put a sudden brake. Already we said about a body which is moving, you stop the bus immediately apply a brake. So what happens? The passengers and all will fall front. Have you seen that one? They will fall front. Why do they fall front? Because they are already on the motion. They wanted to continue to be in motion. So the bus is stopping, but the passengers are all trying to keep on the motion, so they fall in the front. And sometimes even somebody is standing there, they immediately fall so much. In the floor also sometimes they fall down. So the person getting down from a speeding bus falls in the direction of the motion of the bus. All of a sudden, sometimes it happens. So the bus is going, and as the bus moves, the person quickly wants to jump. The bus is already going. His body is already in the motion. But the feet comes to the rest. The feet comes to rest immediately. So what happens here? This person will quickly fall down. I've seen many of them, they just quickly fall down because the feet is just stood straight here. So what I usually do, people do, they will not fall down. They run along with the bus for some direction and then they will stop. So this is called the inertia of motion. The athletes who are taking the long jump, they always run for some distance and then take a long jump. And there's another example also is given here. You can just read this one, all the 4 examples. The next one is inertia of direction. The inability of the body by virtue by which it tries to resist the change in its direction of motion. So suppose you are there in a car. Going in the straight road. So the car is going like this, and all of a sudden there's a curve. So the curve, immediately the car turns like this. When the curve is like this, you as a passenger sitting here inside the car, what happens? You fall this side. Have you seen that one? When the bus is turning, all the passengers will turn this side. Why they are turning this direction? The whole of this passengers are all turning this side because they think they should go straight. Their direction actually it was straight. Bus is turning here. So they continue to tend to go straight. That's the reason everybody is following this direction. That's called inertia of direction. It doesn't want to change the direction. It keeps on going in the same direction. That's the reason all the passengers wanted to say to the bus, don't turn, I wanted to go straight. So they fall this side so that they will continue to. But eventually the bus the bus strength is so high and you have to finally bend back. Sometimes you might have to hold the window so much so that you will not fall away also. So this is the very typical example of inertia of motion. And if you are riding on a bicycle and there is so much of mud, what happens? The mud comes like this. The mud already sticks like this. It comes like this. And the mud takes the tangential path, straight path. So mud doesn't fall down, but it just goes up. And the poor guy who is already wheeling this one, he's all his back shirt. Have you seen that one? Mud is always there when you cycle. Because this inertia of motion, it allows this one to constantly go in the same direction here. So it just comes on the top of his t-shirt itself. Look at this one, mud flying tangentially on the surface of the car tire. So that's the reason they give mud guard. The mud guard is that you don't have a mud guard, then everything comes on top of you. When the bus suddenly turns, already I told, the passengers lean leftwards. Stone, which is tied in one end of the string, revolving in a circle, flies tangentially when it is given. So you have a string and there's a stone here. When you are just revolving this one, as soon as you leave this one, what happens? It starts, if this is the direction of this one, it starts going in the tangential manner because it wants to just continues to go in the same direction where it is. It doesn't want to go in the turned path. So that is the thing. So these are all the various things. Now we'll go to the important part of Newton's first law of motion. What is Newton's first law of motion? You already known this one. Now I'll just read this one. An object at rest tends to stay at rest, and an object in motion tends to stay in motion with the same speed in the direction unless it is compelled by some external unbalanced force to change that state. So you can say the body continues to be at rest or in a state of uniform motion unless and until it is acted by an external force. It is compelled by an external force. The external force is unbalanced force. There could be a balanced force also. Sometimes they say, oh, I have given already a force. Suppose a force is given to this body and say, oh, it has to move. Maybe there is another wall which is there and you're giving a force. How can it move? Because there is another force which is already giving. It is a balanced force. It cannot move. So it is given here an unbalanced force to change that state. So the forces are balanced. Okay, the forces are balanced. It means the object will be at rest or the object will be constantly in motion. You need an unbalanced force. The body at rest means velocity is 0. Acceleration is 0, the body continues to be at rest. The body which is on motion, velocity is not equal to 0, but acceleration is 0, it continues to be in same motion. So that is the thing is, if you have to have somewhere the body has to change this motion or change this rest, you need an unbalanced force is needed. Not a balanced force, you need an unbalanced force to counteract and change. This is Newton's first law. Please learn this one thoroughly. You know this definition, but learn once again, it's important. So Newton's first law talks about a qualitative definition of force, a quality of force, how much a quality which is needed. Quantitative force, how much the amount of force, it will be given by second law. The first law says a quality of force, how much the quality it is needed for the force so that it will be able to change the state of rest or change the state of motion. That's what given here. The next one is linear momentum. Linear momentum. You already heard of studied this one in lower classes. Momentum can be defined as mass in motion. In short, any body, a big body, a mass is there and it is moving. That means it is momentum. Mass in motion, mass in rest is called inertia. So we say inertia is there. So I always say somebody is sitting and one doesn't want to move at all and he has so much of inertia. Somebody is sleeping, he has inertia. Now a mass is moving, any body is moving constantly, this has a mass. That means it should have, definitely when a moving body is there, it will have momentum. A moving body has momentum, mass in motion. So this momentum can be defined as the, so how much, there are two things which is there, two factors, how much mass is moving, how fast it is moving. How much mass is moving and how fast it is moving, velocity. How much? That is basically momentum. So what is momentum is? It is a product of, momentum is a product of the mass of a body and the velocity in which it goes. A uniform velocity in it goes. That is called momentum. Momentum is the product of mass and the velocity of a body. It's called linear momentum of a body. So it is a vector quantity. P vector is equal to m into v vector. So mass into velocity. The unit of mass is kilograms and velocity is given in meter per second. So it is kg, meter per second is SI unit. We know already the dimensions. Dimensions we all know. We have learned this one. So now the first dimension it is coming into application. What is momentum dimension? It is already there. Mass into velocity. So it is there. Now this could be of three cases can evolve out of this. So we will see momentum p vector, it is equal to mass into velocity. This is a scalar and this is a vector quantity. So mass into velocity, it determines like this. So there are three possibilities which is quite possible here. What if when two bodies are moving, okay, two bodies are moving, but both the bodies in case one, so always we are going to see three cases, and all the three cases two bodies are moving. Remember, two bodies will be there to move. The first case is when both bodies have equal mass. That means first body is moving in p1 momentum with the mass and velocity is v1. Second body is moving p2 and having a mass with velocity v2. But remember, both of them have the same mass. So divide both as 1. p1 upon p2 is equal to v1 upon v2. And here mass and mass will be there, you can cancel it. Mass into velocity, these two equations have been divided between each other. So if velocity of one, the first one, is greater than velocity of second one, If this velocity is greater than second one, then what will happen to the momentum? P1 is also greater than P2. This is the case 1. So what will happens here, the momentum is directly proportional to velocity. So if you want to draw a graph for this one, you want to draw a graph, momentum and velocity, you will have a straight line. So let us see this one. So V and here P and mass is equal to constant. So you have a straight line like this. It is proportional, it is directly proportional here. Second case, case number 2. So what is the second case which is possible is, same two bodies are moving. Here both has same velocities, same velocity, but different masses. So P1 has m1 into V and P2 is m2 into V. Divide both this one, P1 upon P2 is equal to m1V upon m2V, and velocity gets cancelled out. So P1 upon P2 is equal to m1 upon m2. So the momentum is directly proportional to mass. Suppose if m1 is greater than m2, the mass of the first body, look at this one, a big mass is there, this is m1, small mass is there, m2. This is also going in the same velocity, this is also going in the same velocity. Both the velocities are same. Which will have more momentum? This will have more momentum or this will have more momentum? Remember, this will have more momentum. Just imagine in an instant, a huge truck is coming, a loaded truck full of load is there. Okay, a truck is going. At the same side, you have a small nano car is going, or maybe an auto is going. Both of them going in the same velocity. This one will be around maybe 1 ton is there, and this one is few kilograms are there, maybe 200 kilograms, very less. Which will have more momentum? This will have more momentum, exceedingly huge momentum, because mass is more, same velocity. So here momentum is directly proportional to mass. So m1 is greater than m2 means p1 also is greater than p2. This also will have a graph. The graph, if you draw for this one, you have here as mass you put here and momentum you put here, and you will have the same line. Velocity is going to be equal to constant. So the second case we have seen. Case number 3. So what is case number 3? The third case is when the momentum is same for two bodies with different masses and velocity. So P is equal to m1 v1, P is equal to m2 v2. Look at this one, mass is different, m1 v2, m2, v1 v2, but momentum is same. Divide this one on both sides. So P upon P is equal to be equal to m1 v1 upon m2 v2. So when you cross multiply, m2 upon m1, this will get cancelled, m2 and m1 is gone here, is equal to v1 upon v2. So mass is inversely proportional to velocity. You get here? So if you want to draw a graph here between mass and velocity, so you put here as mass and velocity. So what will be the graph? The graph will look like this. Momentum is constant. These things you have studied in 9th standard. It's not new thing. But I'm just quickly going over this one because certain numericals can come based on this. Now look at this one. All the three graphs are given here. Mass is going to be equal to constant. Mass is constant here, and velocity, and you get the momentum. So here momentum is constant, velocity and mass, and then you get here velocity is constant, mass into this one. So all the three is there. So you'll be able to get this one. Now the next one is Newton's second law of motion. What is Newton's second law of motion? With this second law, we'll be able to finalize, finish here. After I finish Newton's second law, and then I'll be able to close here. So it says the rate of change of momentum of a body is directly proportional to the applied force, and changes takes place in the direction of the applied force. So it has made a very, very important thing just after we have studied about momentum. Momentum is studied, it is going to be equal to mass into velocity. Now they are making another statement is change in momentum. Okay, you can change the momentum. That means the change in momentum is called dp by dt with respect to time. Now we already know this one as the rate of change of anything with respect to one another is called the differentiation of one with respect to another. So we know acceleration is going to be equal to dv by dt. The rate of change of velocity with respect to time is acceleration. Similarly, the rate of change of momentum is given here. It is directly proportional to the force applied. It is directly proportional to force applied and takes place in the direction of the force. It is a directional thing and is also direction. So rate of change of momentum is directly proportional to force applied and takes place in the direction of force. So that is the basic, the formula itself is given here. So Newton's second law is called a qualitative definition. So first law is called qualitative definition. The second law is called quantitative definition. Look at this one, quantitative definition. So the quantity of force is given here. The rate of change of momentum is directly proportional to the force applied and takes place in the direction of force. For example, you have a stone here, and this stone is already moving. Slowly it is moving. It is already on the motion. Okay. Now all of a sudden you see the stone is moving and you wanted to give a big kick with a boot. You just give a boot it out. You just give a big kick. Maybe it's a ball. It's just rolling on the ball. It is rolling, and you give a kick with a football kit. And what happens? You get a force. The force is so high, and immediately as soon as you give the force, the momentum changes from P1 to P2. The momentum changes. There is a quick change in the momentum from P1 to P2. So that is called the change in momentum. Now, how fast you do it, how much time duration you give, that time is very important. You give it in a short duration of time, very quickly, then more is the force. That means a quick kick will make it to be very, very fast in changing the momentum. The momentum can change very slowly and fastly also. It depends upon the time interval. So within the short duration of time, you give a momentum, that it is very, very important. That momentum change in that very short interval makes it as a force. A force is so heavy. That's the reason the momentum is so quick change within a short duration of time. Suppose from here 5 is the momentum, and then it comes to 50, but it takes 1 hour to change it. That is not a big change, but it just does it within 1 minute. Then that means momentum is changing so quick. That means so great the force will be. Very high force will be there. So that is the way in which it is to be quantitatively understood. The force applied changes the momentum, and also the first thing is the quantity. How much is the amount of the force. Change in the momentum with respect to the short duration of time, that is called amount of force. The next one is the direction of force. Now a football is there, you are hitting maybe in a goal post. You need to kick it in this direction. And the momentum changes in the direction of the force. You just directly, you hit this one here and it goes in that direction. The change in momentum takes place in the direction of the force. So it has a short expression here. You will go ahead and see that very short expression. Momentum is going to be equal to mass into velocity. We already know this one. And we have just saw force is directly proportional to dp by dt, and this is momentum. So we know momentum is going to be equal to mass into velocity, is also momentum, is a vector quantity. Change this momentum and put m into v. So force is going to be equal to, it is, maybe you can put direction itself, d by dt of, now look at this one, differentiation comes here. Differentiation is something which will be constantly going on every place. Mass into velocity, momentum is taken over and then put here. Mass is a constant, so F is proportional to mass will come outside of this one, m into dv by dt. So rate of change of velocity, what is the rate of change of velocity? M into acceleration, because we know since acceleration is equal to dv by dt. So you get here m into a. So F is equal to k times of m into a also, you can say. These are all the vector quantities. K times of m into a. If, in always in SI unit, k is going to be equal to 1. So F is going to be equal to m into a. Mass into acceleration comes after this basic definition of F is equal to dpa by dt. We know force is equal to mass m into a. Mass into acceleration. How does it come? It comes basically from the force is directly proportional to the rate of change of momentum. So you get here finally F is equal to k times of m into a. Moving further down, you can have the SI unit of this one. So F is going to be 1 Newton when mass is equal to 1 kilogram and acceleration is equal to 1 meter per second square. When then k is equal to 1, that means F is equal to m into a. So when mass and acceleration is unity, the force is going to be equal to unit. This is 1 Newton. So this unit is known as the absolute unit of force. So F is equal to m into a. Dimension of force, we already know mlt minus 2. We have seen so many times. So there is another unit called absolute unit. Okay, this is an absolute unit and that's called gravitational unit. There are two units you already studied in the lower classes. What is an absolute unit? Absolute unit is F is equal to m into a. It is just an absolute unit which takes place in any place, wherever it is, irrespective of gravity. So we always take an absolute unit whenever you are doing. We don't sometimes consider gravity. In the whole thing we just consider only acceleration. The body is moving. It is always acceleration. For example, a bus is moving. You have studied all the things about a bus is moving, a car is moving with a velocity, and then there is an acceleration. Hello, this acceleration is only absolute unit only you take. You don't take gravity at all into consideration all the time. Even though we are on the earth, even though there is gravity is there. So there is an absolute unit which is there called just m into a. So it is given here. 1 Newton is going to be equal to 1 kg and 1 meter per second square. And next one is in CGS unit, you can say 1 dyne is equal to 1 gram and centimeter per second square. So the relationship is, we already know it is 10 to the power of 5 dynes. 1 Newton is going to be equal to. Next one is gravitation unit. What is gravitation unit? When 1 kilogram force is applied and it gives an acceleration of 9.8 meter per second square, not 1 meter per second square, it is 9.8. Then it is called kgf. So 1 kg into 9.8 meter per second square, because that is the way gravity is always there. So it is 9.8 newtons. That is called 1 kgf. So that also you would know before itself. So last, before we close, some consequence of the second law of motion. What are the consequences? So the first consequence is it provides a concept of inertial mass. If acceleration is not there, so what happens? The mass will be continuously be at rest. So the mass is so important here. The mass, it is there. The mass of a body is a measure of the inertia of a body in a linear motion. Such a mass which accounts for linear inertia of a body is known as inertial mass of a body. So acceleration, if it is going to be equal to 1, F is equal to m. So F is going to be equal to inertial mass, you can say. The inertial mass of a body is equal to the amount of force required to produce a unit acceleration. That is called inertial mass. A mass, it talks about a concept of mass over here, they call inertial mass. So that's the first part of it. The next second part of it is the second consequence of the Newton's second law of motion is in the next page. It is given here as it is a measurement of force. In the next page, from Newton's second law, if you have m into a is there, it is mass into change of velocity upon time. So by knowing the mass and of the body and measuring the change in the velocity in a given time, the force applied you will be able to see. So that's what it is. It can be calculated. The next one is no force is required for moving body with constant velocity. When velocity is same, no force is required, acceleration is going to be 0, so force is going to be 0. That's the next consequence. You can say the second law of motion is a vector law. We already know F is vector quantity and dp also vector quantity, and mass acceleration also you can do into all the three coordinates fx plus fy and fz, which is I, j and k, and dp also it is a momentum is px and py and pz, and acceleration is ax and ay and az in all the three coordinates. So you can say fx in the x direction, fy in the y direction, and fxz is in z direction. You can say m into az, ax, and m into ay, and m into az. Mass cannot be in direction, but only other things can be having direction. So these are the various things which we have seen. So you can just note down this particular thing, and with this I close. You can read this one thoroughly and learn all the definitions properly, and we'll see the rest of them in the next class. Thank you so much.